In this video, we will focus on hypothesis testing. We are trying to understand how unusual the observations are that we have in a sample when compared to what we would expect in a population. In other words, we are trying to figure out how weird things really are and whether we can make some kind of decision. We want to be able to frame some hypothesis and test the significance of what we are observing. We want to be able to compare means, proportions, and variances for what we are observing, and I'll show you a method to do that. When we are framing hypotheses, we are making a claim about a population parameter, not a sample statistic. We are using a sample and its statistics, but we are trying to understand something bigger about the population. That's what the statistical tests are doing, and why the central limit theorem is so important for us to do inferential statistics. The null hypothesis is assumed to be true, and an alternative hypothesis has to be crafted to test and challenge the assumptions of the null. For example, a new sales force bonus plan is developed to increase sales. The null hypothesis would be that the new bonus plan is completely equivalent to the current bonus plan. The alternative hypothesis says that sales will be higher than the current plan. We will use statistics to understand what that means. The framing of the hypothesis is important, and I will show you 3 different ways that are commonly done. The hypothesis for the null will always be that things are equivalent. The alternative hypothesis will not. In general, we will test if the mean of a population based on the information we have in our sample is different. Let's go through them. If we continue with our bonus example, here is how we would frame the hypothesis in the first instance. Under the current sales plan, let's pretend the average daily sales is $1,000. The new sales plan is to increase that average. The null hypothesis would be that there would be no difference. How this would show up is that the new sales plan would be underperforming or equivalent. Underperforming or equivalent, as you can see here. If any of these results show up, we will know we are in the null hypothesis situation. Alternatively, we would need to see that sales have increased above $1,000 to accept the alternative hypothesis that the new bonus plan is improving sales. There is another alternative, which is that perhaps under the current plan, the null hypothesis is that the sales will stay the same. However, it could be that with the new plan, sales might go down. In this case, we would still reject the null hypothesis if this result showed up, and we could collect enough evidence to suggest that this is the case. We could look if the new plan caused sales to decrease. We can put all of this together in a two-tailed test, which is the third way of framing the hypothesis. We could say we don't know what could happen. Under the current plan, the sales are $1,000 per day. We just know that the new plan could change that. The operative word here is change, rather than decrease or increase sales. We are looking for a change between the sample and the population. The null is therefore that there is no change, as you can see here. The alternative hypothesis is that something other than $1,000 is found with some significant level. So looking at the 3 ways of framing the hypothesis, we can see that the null always has some kind of equivalence, right? equivalent, equivalent, equivalent. Even though it may be greater than or smaller than, there is still an equivalence statement being made. Certainly, the two-tailed test is really an equivalence. Now, all the alternatives don't have an equivalence in their framing. So this is how we may think about this visually if we plotted each framing. So in the middle distribution, we have my current sales plan with an average of about $1,000 of sales per day. The other two distributions are the ones we care about understanding because they reflect what happens with the new sales plan. So if the new sales plan increases sales significantly, we have a new population. The mean is so far away from the original mean that we can conclude that the sample came from a different population. In the alternative, the new plan decreased sales somewhat, right? The mean is a little bit lower than the current mean, but the difference is weak. And we know it's weak because there is very large overlap between the two distributions. So if we put this into words again, different sampling distribution means are not as close together when the null hypothesis is false. We can reject the null hypothesis and conclude that there is support for the alternative hypothesis. The new sales plan significantly increased or decreased sales. Now let's compare that to the situation that we see here. If all of the means are clustered together like this, around the original value of $1,000, we can see that there is no significant difference between the new and the current plans. Based on our sample, we have no evidence of operating outside of the population. We cannot support the alternative hypothesis, is how we would interpret this situation. So now we come to the matter of significant level. We already talked about this a little bit, about how we may look at the significance level at 0.5 in the case of a two-tailed test, where we would need to look at the upper and the lower proportions of the tail. In this case, our z-score would be 1.96. And we would use that to measure. The interpretation in this case, if you kept sampling over and over again, 95% of your samples would come from this area. In our example, the interpretation would be that if my sales resulted in a z-score that fell outside of the z-score, I can reject the null hypothesis. The sales in this case could be significantly different in the upper or in the lower end. I could have practically no sales or enormous amounts of sales. And in either case, the situation would be unusual and suggest we are talking about a different population. Now let's look at the other situation, where my sales plan will increase sales. And here I could say we can use a one-tailed test. So the hypothesis is only that the new plan will increase sales, right? So something important here changes because now I have to use a different z-score, right? This is a one-tailed test and my z-score is now 1.645. It is in fact easier to get this z-score than for the two-tailed test. A one-tailed test allows me to look only at one tail. Now, this is a picture of what I just described. Here is my current plan. The other is the new plan. Now, the difference would tell me whether it is significant. There are other examples we could imagine which may be easier. For example, the average height of professional basketball players versus non-professional basketball players, right? We can imagine one is here, the other is here. Or patients that are taking an effective therapy versus a control group, which is getting no therapy. Or we could think about the levels of superpowers present in the Justice League versus everyone else. So another thing to think about is p-values. P-values are a way of looking at the probability that is related to the confidence interval. Now, when we think about p-values, we need to look at a statistic called alpha, which helps us interpret and in a way is easier than the confidence interval. Alpha relates to those regions under the curve at the tails. If the p-value is less than or equal to the level of significance alpha, the value of the test statistic is in the rejection region. We reject the null hypothesis if the p-value is less than or equal to alpha. If the p-value is less than alpha, the difference measured is significantly different than the null hypothesis. There is a statistical evidence supporting a significant difference in the level of confidence, which, for our purposes, we are looking at 0.05 or less. So here are some guidelines for interpreting the significance. P-values that are less than 0.01 indicate there is strong evidence to reject the null hypothesis. P-values in these ranges would be acceptable evidence. In these ranges would indicate weak evidence, and anything that would be greater than 0.1 would be insufficient evidence to reject the null. So here's one way to interpret what I just said. If we are looking at the confidence level of 0.1, it means there is a less than 10 in 100 chance of observing a result in the range if the null hypothesis were true. In other words, there is a 10% chance of observing a result in the range if the null hypothesis were true. In the case of 0.05, here we're talking about a chance of less than 5 in 100, or 5%. In the case of 0.01, we're talking about 1 in 100 chance, right? So this is how we would interpret those values. Now remember that significance does not indicate causation, nor does it indicate effect size of the difference. Since this is a probabilistic exercise, we have to be concerned with the possibility of errors. We could reject the null hypothesis falsely. If we do that, we have a false positive, where we have claimed a difference when there is none. This is a type 1 error. For example, we may have concluded that sales have improved when in fact they have not improved. The other type of error is type 2, when we accept the null hypothesis even though it is false. We have a false negative and we miss a difference when there is one. The example here would be to conclude that sales have not improved even though in fact they have. In other words, we have missed an opportunity. There are 3 different tests we can refer to. The first is the z-test, which assumes we know the population variance. But since we don't always know that, we will need to look at other types of tests. One is the t-test, which can be used when we don't know the population variance, as it uses the mean of two groups. And the third is the chi-square test, which looks at the significance of differences between proportions of variances of two or more groups. So in summary, statistical inference is all about determining when some observed result is rare based on chance alone. We should frame the null hypothesis as an equality, as if we are expecting no change or no difference. We can reject the null in support of the alternative when our observations reach or exceed significance. The z-scores and t-tests are used for testing mean differences. The chi-square test is used for proportion and variances. Here is an objective checklist, and if you want to see more, look at this YouTube video.